Okay, well, I think let's start. It's my great pleasure and honor to introduce Lexing Ying, who already gave the first of his 3 lecture series yesterday. And today he will continue with his lecture series, and he will talk today about solving inverse problems with deep learning. And I think we are all very much looking forward to that. Lexing, the floor is yours.
Okay, thank you, Gita. Yeah, today I'm gonna, the second talk is about solving inverse problems with deep learning. So this is joint work with Yu Fan, Yu Haoguo, and also Cindy. Okay, let me get started. So this talk is about inverse problem. So an inverse problem is essentially the task is to discover internal structures from boundary measurement. So here I give you 3 pictures. So on the left-hand side, you have the picture of radar imaging, where you're trying to, the radar send out electromagnetic wave. And then based on this, the wave, the echoes, the reflected signal, you're trying to detect the shape and also the speed and various kind of properties of the moving target. So in the second picture, the seismic imaging, and the signal is, you see the ship, and it has these so-called shotguns, which is air guns, send out the different acoustic waves. And the acoustic wave propagate through the media and get reflected at the internal of the Earth structure. And the reflect signal is recorded on these like cables. So, and from the recorded signal, one is trying to infer the internal structure of the Earth. And finally, on the right-hand side, you have the picture of a medical imaging device where around the chest of a kid, one place a certain electrodes to apply certain voltages, different profiles of voltages, and by measuring the current, and you'll be able to understand whether the child is healthy or not. So there's a lot of inverse problems. So here I just listed a few: far-field imaging, seismic imaging, electric impedance tomography, travel time tomography, and optical tomography. Now, mathematically, to make it more precise, so in all these examples, inverse problems, we have something called a boundary measurement, which I denoted throughout in this talk by D. And from the boundary measurement, what you want to do is that you want to figure out the internal parameter, which would be consistent denoted by eta through this talk. Okay. Now, inverse problem is a very challenging task for 2 reasons. So one reason is that it's often yield conditioned. For wave-based imaging, usually the yield conditioning is not such a big issue. But for things like electric impedance tomography, where it's based on diffusion, the yield condition is a serious issue. The second main difficulty is that we are interested in the whole inverse map. So it's a map from D to eta. So therefore, it's a very high-dimensional object because the input is a high-dimensional field D, and the output is also a high-dimensional field, and the process is nonlinear. Now, what we're trying to do is we're trying to use deep learning to help us to solve inverse problems. Now, I think by now everyone's familiar with deep learning, so I don't need to say too much. But from the mathematical point of view, I think the main reason why neural networks, deep neural networks, are very attractive is because it provides a very flexible way to represent high-dimensional functions and maps and distributions. So here we're going to use it to represent the high-dimensional map, the inverse map. Okay. Now, there are several challenges when we try to use a deep neural network to represent the inverse map, which is from the boundary measurement to the interior property. So here are the 2 key challenges. The first is that in inverse problems, typically the amount of data we have is much more limited compared to traditional AI tasks like image classification, also language understanding. So part of the reason is that getting these data is more expensive in inverse problems because you really have to build the device, you have to collect the data, you have to clean up the data. And second is that for privacy issues, usually it's very hard for different entities, organizations to share the data. For example, it's very hard to imagine that different oil and gas companies are willing to share all their seismic data together. And second is that in the inverse problem, in many cases, not only we are interested in the classification problem, we're not only interested in yes or no answer, we're actually much more interested in, for example, getting the quantitative number. So it's a regression problem rather than a classification problem. So in order to get the number actually more accurately, so it's a more challenging task compared to classification. So the accuracy criteria is higher. So here's a plan of how we're going to address this issue. The first, how to address the issue of using deep neural network to solving these problems. So we're going to use mathematics and physics to help us design the new modules of neural network. So as you will see that all the traditional modules of deep neural network is based on certain mathematical structure. Here we're going to study what other structures appear in deep learning, what the mathematical structures appear in this problem, and try to use them to motivate the new neural network modules. And then what we're going to do is that we're going to use, again, mathematics and physics to assemble these different modules together to get an architecture for our neural network. And finally, we're going to train end-to-end with a limited amount of data we have. Let me clarify that the neural network we get is usually not very large, and the number of parameters is not very high. So we're not really in the so-called over-parameterization regime. Part of the reason is that because we wanted to make sure that our model itself is parsimonious so that we get some regularization so that we don't need to worry too much about overfitting. Okay, so the application we're going to consider, so here's the application listed. Okay. Now, so the outline of the talk is the following. So it has two parts. The first part is going to introduce a few new modules. And then I'm going to move on to a few applications in these problems. So new modules. So as I mentioned, if you take a look at the mathematical structure behind the neural network, you will find some very familiar objects. So here on the right-hand side, I listed the popular neural networks, starting from fully connected neural network, convolution neural network, residual neural network, recurrent neural network, and residual neural network. Now, the corresponding picture is down here. Now, if you study the mathematical objects behind these neural networks, you will find familiar objects. For example, fully connected neural network is really based on dense operators. CNN is based on translation invariant local operators. Recurrent neural network is based on Markov chains. And the residual neural network is based on ODE, or rather discretization of the ODE. Now we ask ourselves, if we are starting to solve inverse problems using deep learning, what kind of operators are important for deep learning? So what are the operators which are important for inverse problems? And based on the operator, what can we construct? Now there are two types of operators that are very important for inverse problems. One is called a pseudo-differential operator, and the other is called a Fourier operator, Fourier integral operator. So Fourier integral operator plays a big role, for example, to represent the forward map of the wave-based imaging, or the adjoint map of the wave-based imaging. And the pseudo-differential operator is characterized, for example, the normal operators. Now, so what I'm going to show you is try to build the neural network modules based on these operators. So let's first take a look at the pseudo-differential operator. So I'm not going to go into the mathematical detailed definition, precise definitions, but this is roughly the definition of the pseudo-differential operator. It's a generalization of the differential operator, as the name tells us. So it can either be written as an integral form when you have the kernel k here, or you can write it in the Fourier form. So compared to the usual inverse Fourier transform, the difference is that instead of having, you have this so-called amplitude function, which depends on not only on x, but also depends on the c. And the amplitude function is usually assumed to be smooth in x, and also smooth in c away from the origin. Now, pseudo-differential operator, as I said, play a big role. They represent the Green's function. It also includes the normal operators in inverse problems. One important property of the pseudo-differential operator is that it keeps the singularity local, meaning that if I have a function f have the singularity at a certain location, when you apply operator a to it, the location will not change. It will only disappear, but it cannot create new singularities. Now, the question we care about is how do we build a neural network module based on the pseudo-differential operators? So our plan of attack is to start from something called a sparse representation of the pseudo-differential operator. And based on that, we're going to try to construct a linear deep neural network. Why linear? Because the pseudo-differential operator itself is linear. So we're going to start from a linear neural network. And then what we're going to do is that we're going to put ahead of the machine learning expert practitioners and try to extend this linear neural network to nonlinear networks by adding certain activation functions. So first step is this sparse approximation. Now, how do we find the sparse approximation of pseudo-differential operator? Well, one important property of pseudo-differential operator is that if you view this as a matrix, for example, after you discretize, the off-diagonal blocks of the pseudo-differential operator are typically smooth and also numerically low rank. Now, there are several ways to exploit this structure and to design sparse representations. The way I'm going to use here is based on wavelet transform, and more specifically, the wavelet transform in the non-standard form. All right, so here I'm just giving you a picture to illustrate the main idea. Suppose you give me a pseudo-differential operator and assume that you discretize it with n by n points. So n points, so therefore it becomes n by n matrix. The non-standard form of the pseudo-differential operator, which is proposed by Bell, King, Koifman, and Rockling almost about by now 30 years ago, is to represent the pseudo-differential operator in the so-called redundant wavelet and a scaling function frame. So typically, most of the cases when we use wavelet, we use it as orthogonal transformation. But here, not only we're going to introduce wavelet, we're also going to include the wavelet along with the scaling function that you use to build this wavelet. So the price we have to pay is that the matrix increased by size increased by a factor of 2. So under this scaling and also function wavelet representation, now the original matrix of the size by size n now becomes a matrix of size 2n by size 2n. So the first matrix and the last matrix correspond to this redundant wavelet transform. And the beautiful thing about this is that if you take a look at the matrix, it has a very nice sparsity pattern. So in fact, the number of non-zeros in the middle matrix is always order n, if you, with a constant depending on the thresholding value that you care about. Now, it also has a very nice structure. It has a so-called finger pattern. And at the coarser scale, it only has roughly around 3 diagonals, banded 3 bands. And then you go to next scale and also have 3 bands and so on and so forth. And the different bands, because of this redundant transform, doesn't have interaction. So it's all 0 here. Now, what we realize is that if you take a look at this, apply this matrix to a vector, so corresponding to apply this gray matrix to a vector, apply this right-hand side to a vector, then this matrix vector multiplication can be decoupled into different levels. At every level, so for example, at the first level, it's corresponding to, just use a different color. At the first level, it's corresponding to using these 3 matrices multiplied by a certain vector. And this is what I wrote down here. And in this case, it's not hard to see that the whole computation of this matrix vector multiplication at this scale, at this level, can be written as a neural network with 3 layers. So the first layer is multiplying this matrix to my input vector. It's corresponding to a convolution. The reason why it's a convolution because it's a wavelet transform. So it's a convolution which turns into 2 channels. And the middle step is corresponding to, again, a convolution, turning 2 channels to 2 channels. And the last step, which is multiplying the leftmost matrix, is corresponding to turning this 2-channel signal back into 1-channel signal. So it's all convolutions. So once you realize that, we can chain different levels together. And this arrow down here and up here corresponding to the wavelet operator, which moving between different scales. And if you chain everything together, this will be architecture of a matrix vector multiplication under this BCR framework. Now, to make it more powerful, what we simply do is by inserting a few more internal convolution layers at the different levels, and also by adding Raoult's activation to make it more nonlinear. Okay, so this is what we call BCR net. So BCR is the initials of the Belkin, Kaufman, Rockling, who invented this non-standard wavelet form. So the second module we're going to talk about is based on Fourier integral operators. And the Fourier integral operator take this form. Sorry, I forgot. It's supposed to be a hat here, but the Fourier integral operator take this form. So compared to the Fourier transform, and also rather compared to the pseudo-differential operator, the main difference now is that not only I have this amplitude, I also change the phase function. Previously, just x dot c, but now it's a phi x c, where phi is a function smoothing x and homogeneous of degree 1 in c. Now, the Fourier integral operator is very important for wave propagation in variable media. It represents the parametrics of the wave equation. Instead of just keep the singularity at where it is, what the Fourier integral operator does is that it moves the singularity along very well-defined way. So what's encoded here in the phi function is something which is called Hamiltonian flow, and this singularity just essentially move along this Hamiltonian flow. How do we build a deep neural network using these Fourier integral operators? Well, again, we're going to consider sparse representation of approximation of the Fourier integral operator, and then generalize it by adding more layers and adding values. The sparse representation tool that we're going to use is something which is called butterfly factorization. And here's the main idea of the butterfly factorization. Now, suppose you give me a Fourier integral operator of size n by n, okay, after discretization. The operator itself is not low rank, and its off-diagonal block itself is also not low rank. Just think about the Fourier transform, because the Fourier transform is an isometry, so it's not low rank, the whole matrix. And if you take the half of the off-diagonal block, half of the matrix, half size the off-diagonal block, it's also not low rank. But what is low rank is a very special partitioning. So if you, let's again say that this is a matrix of size n by n. Now, if you chop this matrix into square root of n by square root of n blocks, where each block is of size square root of n by square root of n, and then each of the square root of n blocks itself is going to be numerical low rank. So it's kind of like the second best thing, okay? So what I'm showing here is that if you take each of the block, for example, this one, you can do a singular value decomposition or any low rank approximation you want. This block itself is going to become the column matrix times a small core matrix and times the row matrix. So this picture is really showing that I'm performing low rank approximation to each of these blocks. So this is visually it's very appealing, but in terms of operations, it's not very easy to work with, in fact. So therefore, what we do is that we rewrite this as a product of the three matrices. So the first matrix is really collecting all these column blocks, like tall skinny matrix at every row, and put them together into one single matrix. And the second matrix here corresponding to the columns here. Now the first matrix at the end is corresponding to these rows. I'm just going to stack them together. And the same works for the rest of the diagonal blocks of the third matrix. And what's interesting thing is about the middle matrix. The middle matrix has a very special non-zero pattern. And in fact, what it does is that the only non-zero entry is correspondent in the ith block, jth location, is associated, for every row in ith block and jth index within the block is in the jth column, jth block and ith column. Okay, so in some sense, it's kind of like doing transpose. So let me suppose this is ith block and this row is actually jth row within the ith block. Then the only non-zero entry location here is corresponding to the jth block, and within the jth block is ith column. So in some sense, the ij index of the row numbering become the ji index of the column numbering. So it's like a switch of these two indices. Now we ask ourselves, how do we represent the matrix vector multiplication of this butterfly factorization in terms of the neural network? So what it turned out is that this structure. So in the first step, it's corresponding to multiply this with the column vector. Now you see that it really, what it does is that it turns this, it's kind of like a local convolution, because all these outputs is only going to be associated with the first chunk. So what you get is that you turn a size n vector into a size n by square root of n by square root of n block. So all you can, in the neural network language, software language, it turn this into a signal of length n, but with square root of n, but the square root of n channels. So this is the first step. So the second step, which is multiplying this very sparse matrix, and you recall what I said is that it turning ij index to ji index. So therefore, once it is represented in this multi-channel version, and multiplying ij to jl is essentially correspondent to the transpose. So because you turn the block into the block index into within block index and vice versa. So therefore, ij becomes ji. And finally, multiplying the last matrix is corresponding to expand this square root of n by square root of n tiny matrix into a vector of size n. Okay. Now, so what I want to mention is that this is actually very closely related to something which is called attention mechanism in neural network design, which has become very popular in recent years. So in fact, it's really in attention design, you also have this transform operation, and but if you take a look at the details, what's the only difference is that maybe let me postpone this discussion after I tell you this figure. So once I get this architecture, which is corresponding to linear neural network corresponding to the Fourier operator, so we make it more general by inserting a few ReLUs and a few internal layers. Now coming back to attention mechanism, so the only difference is compared to here with attention mechanisms is that attention mechanism is doing, you can think about it as taking an image, doing a linear transformation in row space and doing linear transformation in the column space, and then do ReLU. But what we're doing here is that we're doing the linear transformation in row space and then do ReLU and then do the linear transformation in column space. So there's a slight difference, but it's very related. Okay. Now, with these two modules available, one is based on pseudo differential operator and the other is based on Fourier operator. And now what we can do is we can start talking about applications. So in the rest of the talk, I'm gonna talk about the two applications. One is so-called far field imaging, and the other is called travel time tomography. Okay, for each of these applications, the workflow is roughly as follows. So we're gonna study look at the inverse map from the analytical point of view, and then based on this analytical point of view, we're gonna design neural networks. So the way we actually going to design neural network is based on perturbation theory, and more importantly is something called a filter back projection. Okay, so what we're going to do is that we're going to write down the filter back projection operator for each of these inverse problems, and then we'll try to represent each operator appeared in the filter back projection using neural networks. Now, our hypothesis is that what we believe is that the neural network can automatically kind of based on the data, figure out where to do linearization, where to do the perturbation. And and at the same time, also figure out what are the coefficients and weights appear in the different terms of the perturbation series. Okay, so the components we're going to use are really three very simple things. One is this BCR net I was talking about, and the second is this switch net for the Fourier operators. And finally, it will only based on, and it will based on the convolution layers. Now, so in each of the case, what we're going to do is that we're going to train the neural network weights end to end with the limited amount of data we have. And finally, once it's trained, then we can just use neural network for future predictions. So you can give me any boundary measurement, and the neural network will take this boundary measurement, crank in the numbers a bit, and spit out the field of internal parameters. So before I go into the details, I just want to say that deep learning for inverse problem has become quite a large field. And in recent years, in recent 3 or 4 years, there has been many papers appear. So starting from the review articles, where many people in the audience, I believe, has involved in, and also micro-local analysis based on the approach based on micro-local analysis, which is very close to what I'm going to explain to you. And also there are also approach based on linear inverse problems, which is very much related to compressive sensing, and there's also this big field of using this algorithmic unrolling approach, which I also briefly mentioned yesterday. Okay, and finally, I also want to mention that recently there's a lot of interesting studies about the stability of this applying inverse problems to deep learning. Apply deep learning to inverse problems, and especially its implication in medical imaging. And I think this is a very important field, and we really need to address stability. Now, related to the work I'm going to describe here is that what I want to claim is that I want to point out is that the neural network that I'm going to propose usually does not have too many parameters, usually have a small number of parameters. So therefore, in some sense, we're still under the parameterization regime. So therefore, that provides some regularization. So therefore, the stability issue is not as severe as some of the networks reported, and that has been studied in these papers. So these are papers study several neural networks and pointed out that they are not really stable. But for us, I think it's a lesser issue. All right, so far-field imaging. Okay, so here's a problem, far-field imaging problem. Let me just describe the physics a little bit. So you have a certain domain, region of the domain of the space called omega, and we assume that in omega there are certain barrier or scatters, which has a scattering impact defined, showing by these gray shapes. Okay, now the physics is described by this equation, so-called Helmholtz equation. So the Helmholtz equation is really the wave transferred into the frequency domain. Okay, so in the Helmholtz equation, it essentially has a Laplacian applied to field u, and also there's a minus omega square over c square times u, has to be equal to 0. So the u here is my total field, and the omega here is called a time frequency, and cx is the unknown sound speed. Okay, so the cx inside is unknown. So even though, I mean, cx is what we usually study, but in terms of calculation for this specific setting, it's usually much easier to transform cx into another quantity essentially called what I will call the perturbed slowness. So in some sense, a perturbation of the slowness. But it's not a standard terminology because it's also being scaled by omega square. So let me not give it a name. Let's just call it eta. So eta is defined to be omega square over c square, cx square, minus omega square over c0 square, where c0 is some kind of background velocity. For example, if you think about the propagation of acoustic wave in the air, you can think about it has a background velocity is determined, unless you study there's a strong variation of the density of the air. Okay, now the total wave field has two parts. The first part is a so-called incoming wave. So this is my detection signal. This is the signal I send it to this object, right? So I want the wave field to bounce at this media scatters and then try to study what is the scattered field coming out of the domain. Okay, so this is the incoming wave, and there's a scattered field that I just drew earlier, a few seconds ago. It's called USX. So the reason why I use USX is because I want to make sure that the scattered field itself depends on incoming direction S, the source direction. So therefore, I subindex with S. Now, the scattered field, how do I collect the boundary measurement? Well, in this setting, typically the boundary measurement is assumed to be collected at very far distance. So you have some scatter over there, here, and here. So what you record is actually not the scattered field. So this is the scattered field, but a scaled and also modulated version of the scattered field, which is called far-field pattern. Okay, the reason why we do far-field pattern is because it's a little bit nicer because it's an order one quantity. No matter even you collect it at infinity, it has been appropriately rescaled, so that's order one, and also remove some linear phase, so the signal itself becomes slightly more smooth. So the boundary measurement is actually the far-field pattern starting from any source S and then collected at all possible receiver directions. So therefore, this is a function which is defined on unit circle in R. So R is also a unit circle, S is also a unit circle. So therefore, the D is a signal that's defined on two-dimensional torus. Okay. Now the inverse problem is that starting from this so-called far-field pattern, what we're going to do is we're going to figure out what is the internal material property, which is eta here. So in order to motivate the design of the neural network architecture, what we do is that we starting from this forward map, which is the map that maps the media perturbation eta to my boundary measurement. Okay. So in the linear regime, what we can do is that when eta is small, what we can do is that we can write down what this operator is. So in fact, this operator is approximately given by this form, okay, up to a constant or smooth amplitude. So what you see is that this looks very much like a Fourier transform. Okay, so in fact, it is like a Fourier transform because it's a Fourier integral operator. So here's the theorem. We can show that this itself is a Fourier. This itself is kind of like a Fourier integral operator in the transform coordinates, and it does satisfy this criteria for the butterfly factorization, in the sense that if you take a look at the map from omega, which is my parameter domain, my unknown field parameter domain, to this data domain. Okay, And this map itself is not numerical low rank. But if I chop my domain, like what did I earlier for the butterfly factorization, if I chop my domain into small blocks, okay, so in the source domain, I chop it into small blocks. In the target domain, I also chop it into small blocks. And then the interaction between each of these two blocks is going to be numerical low rank. Okay. So therefore, you also have a butterfly factorization, but now it's a two-dimensional space-based butterfly factorization, which that can be used to approximate Fourier integral operator. Once we know that, then we can use the switchnet, the one just I introduced for FIOs, to represent the operator A, the forward map. So now we also try to represent the adjoint map, because if the forward map is FIO, the adjoint map itself is also FIO. So therefore, the adjoint map can also be represented by the switchnet. Now, to study the neural network architecture for the inverse map, so as I said, our starting point is this so-called filterback projection. So the filterback projection is very easy. It's just a regularized inverse. So again, motivated by the linear regime, when the eta and d are small, the eta can be actually written as a pseudo-inverse of applied to A star d, pseudo-inverse of normalized operator applied to A star d. So, the regularized inverse. So therefore, this is really the pseudo-inverse of the operator A, okay, with epsilon regularization. So this is the typical formula you see when you learn the pseudo-inverse, right, in linear algebra. If you put limit epsilon go to 0, this is pseudo-inverse. So if you take a look at this formula here, it takes D and apply two operators on top of it. And the first operator is A star, so we know that it's a Fourier integral operator. So therefore, we can use switchnet to represent that. And the second operator here itself is a pseudo, because it's an inverse of the normal operator of the Fourier integral operator. So it's a pseudo differential operator. So therefore, we decide to use the BCR to represent that. Okay, it seems that there's a question in the audience. You can go ahead and ask question, Yuri.
Okay, thank you so much. I've got a very short question. Some people who have been working on roughly similar things, they did two different networks to approximate A and its adjoint. Because
sorry, I couldn't hear very well.
I mean, the connection is really bad. I mean, do you have a microphone in the audience which you can use or something like this?
There is no microphone. We were promised that we will be heard anyway. Can you hear me now? I'm speaking a bit louder.
Yeah, it's better. It's better. Yeah.
Okay. Some people who worked on similar things when they learned the forward operator and an adjoint, they noticed that they needed two different networks and two different sets of training data for the forward operator and for the adjoint, because if they learned an approximation of the forward operator, then the adjoint of it would be a bad approximation of the adjoint of the true operator. So I was wondering if you had this problem too, and if you had to use two different switches to learn A and A star.
Yeah, let me, right, good question. Then I'll explain this. So in fact, the way we use it, we don't train the adjoint operator directly. So because adjoint operator here is only appearing in the design of the neural network. So actually what I'm gonna come into in 1 minute is that based on this formula, we're gonna sample the whole map for the inverse operator, and then we train for the inverse operator. So in some sense, the short answer to your question is that we don't directly train the adjoint operator, but we train the forward operator and the inverse operator. And these two networks are slightly different and has to be trained differently.
Thank you.
Does that answer your question?
Yes, I think so. Yes.
Yeah.
There's another question by Ozan.
Hi. So maybe it's weakly related to what Yuri was asking about. So your argument that A star is a Fourier integral operator, that motivates the switchnet architecture, right? So that's my understanding.
That's right, yes.
And then you go back to mathematics again, and then you say if A star is a Fourier integral operator, then this expression A star A plus epsilon, the inverse, the filterback projection inverse is a pseudo differential operator, which kind of motivates the BCR net, right?
That's right, yes. Yeah.
But if you replace, of course, you don't, as you said, you don't explicitly replace A star with switchnet. That's my understanding, right? Because then it's not a new thing. It's not a
No, SwitchNet itself is, at this point, you can think about it as like CNN, it's architecture, and the weights has not been decided.
Exactly. So okay, wait.
So,
Well, because
so
once you go to SwitchNet, it's not a Fourier integral operator anymore, right?
sorry, no, for SwitchNet.
Once you replace A star with a SwitchNet, it's not a Fourier integral operator anymore.
It is Fourier integral operator. It's SwitchNet is really linear algebra or representation.
Oh, sorry. Okay.
Yeah, SwitchNet is really a linear algebra realization of these of the butterfly algorithm, which is a Fourier integral operator.
Okay, I'm sorry then. Okay, thank you.
No problem. Yeah. Okay, so thanks for the questions. So what we do now is that we know that this itself can be represented by SwitchNet, and this can be represented by BCNet. So what I do is I just concatenate that together. So from my input, I apply the SwitchNet to implement A star, and to apply the BCRNet to implement this, and this will give me the result. Now, so far, I only have architecture. It's like someone told you that, hey, I'm going to use a convolutional neural network to apply, to do an image classification task. But I haven't told you anything about the internal weights of this neural network. This needs to be trained. So final step, which is also probably the most important step, is that all the neural network parameters inside the SwitchNet and BCRNet will be trained end-to-end using the given limited amount of data. So here I'm going to give you one example. Is that it's a simple example. So here the operating frequency is 60, and the domain is a unit box. And I sample the box with about 80 by 80 points in this example, in this calculation. And the data, the boundary measurement that I receive is as I said, is on a unit torus. And again, it has 80 directions, angular resolution. It has 80 discretization points around the circle. And the media I use here is not complicated. It's a mixed Gaussian model. So for every media, you have a bunch of Gaussians. And the amount of training data that I collected is about 12K training pairs. So and also there's another 12K testing data which I reserve for check the performance on neural network. So here's how I carry the test. So this is the ground truth media, which I hide it. So this is okay. So this is already the testing stage. So what we have is that we have something look like that. So in the testing data, sorry, the training data is something the pairs look like that. You have the media eta and you have the D. Okay, then I use that to train neural network. In the testing stage, I will give the neural network my D. So I give the D test. Sorry, D. Yeah, I give the ground truth D. So let me not write D test. I give this D to the neural network, and the neural network is the network I trained will try to infer what would be the media eta. So this is eta n obtained by neural network, and then I compare this eta n with the eta, the ground truth eta that I use to generate this data D. Okay, so this is how I do the comparison. So and you can do the same thing for the forward problem in a similar fashion, but here let's focus on the inverse map. So if you measure the error, the relative error of this eta neural network minus eta, and this is roughly about 1% in these cases. Now with noise, the performance is going to deteriorate, but here I'm only showing you the clean without the case without the noise. So I mean, so these are the data that we collected back more than a year ago. So the examples here are a little bit simple, and also I guess in retrospect we should have included the test with different shapes and different orientations, more complicated structures. There's and these structures have been studied in the literature, and but nevertheless this shows that and that the simple architecture that I propose can do a pretty decent job in recover this is a no media. So the second example I'm going to talk about is something called a travel time tomography. So in the case of the travel time tomography, and the physics setup is the following: is that so we have the equation that describes the physics is something called the Icono equation, which is given by the formula here. Okay, now what is the physics? So here we are in the cartoon world of the 2D. So I would like to use the Earth as an example, but really the example here, the picture is 2D. So think about this in an Earth, 2D Earth, okay? And what we want to do is I want to figure out what is the internal structure of the Earth, of this body. So the data that we collect is, you can think about, you can collect, you can start different kind of like a seismic vibrations at different point close to the boundary. And then the seismic vibration is going to propagate it through the Earth and then go to the seismic stations at different other points. Now, the travel time from one seismic source to a specific seismic station that you can record, the total travel time actually depends on the internal media. Okay. So the experiment, the way we do that is that starting from each of the boundary point, we start a seismic signal. And then for every seismic stations, again, on the boundary of the Earth, we detect how long does it take for the seismic signal to go to different boundary point. Sorry, to go to different boundary point. Okay, how long does it take to go here? How long does it take to go here? How long does it take to go here? And this data will be collected for all the seismic stations and for all the seismic source and for all the seismic stations. Okay, this is the data. So so this is how the physics, but mathematically, this travel time satisfies this equation, which is called Icona equation. This grad U. Yes.
I think there's a question, I mean, by Yuri in between. So.
Oh, Yuri, hi.
Well, I can wait. The question was about the training in the previous slide that you had.
Okay.
Oh, I see.
Yeah.
That's why it's late. Sorry.
Okay. Yeah. So, okay, great. Thanks. So I'll answer that question, but let me just explain this example. So, all right, where was I? Okay, so we have satisfied this Icona equation. So U is actually describe the travel time. The gradient of U and then take the modulus is equal to 1 over Cx. So 1 over the sound speed. Again, I play this trick. The C itself is not easy to work with. So what I do is that I turn the unknown field. I define 1 over Cx to be 1 plus eta. And eta is going to be my new unknown field that I'm going to work with. Okay. Now, recall that I said that my seismic vibration can come from different source point on boundary. So therefore, I'm going to use U superscript S to denote that this is a Icona equation solution starting from the seismic source, starting from the location S. Okay. Now recall, I also said that I can record these U solution at every boundary point. And this tells how long does it take for seismic vibration from S to travel to point R. So therefore, USR collectively give me this so-called total travel, which is the complete travel time information, right? From S to R. So this is my data. Now the inverse problem now becomes, how can we take this boundary measurement, and these are all on the boundary. Again, this is the data is defined on a torus in this 2D example. How can we recover the internal media property from this boundary measurement? Okay. So we do the same thing. We starting from the forward map. So we take a look at that. Suppose we know eta. Okay, we don't know eta, but suppose we know eta. How does the D depend on eta? Again, we are going to use perturbation regime, linear regime, as a motivation. Now, so what turned out is that due to the rotation symmetry of this problem, we can actually, the problem become much easier. If you look at the slight perturbed transformation, parametrization. So recall the D itself is my boundary measurement, is parameterized by R and S. But instead of looking at R and S variable, what we're going to do is that we're going to look at it in the S and H variable, where S is still the source, but H is the difference between R and S. So it's the shift in the angular direction, okay, between your receiver and your source. And then for the eta, which previously was in the X domain, right, in the Cartesian domain, but now let's do it in the polar coordinates domain because of the rotation symmetry. Once you do these two reparameterization of my eta and a reparameterization of my data, and this data actually depend on eta in this very nice way. So in fact, you have two integrals. One integral is in rho, which you can more or less, this integral in rho, which you can think about as a parameter. So you can think about this as a parameter, rho as a parameter. And h you can also think about as a parameter. But once you think rho and h as a parameter, the remaining thing is actually a convolution in the s and the theta variable. So because s appears here, let me use a different color. S appears here, theta appears here, and here you have s minus theta. So really, it becomes a bunch of a 1D Fourier transform and then do the integration on top of that. Okay, so it's a 1D integral Fourier transform with many channels. Now, once we know that it's a 1D Fourier transform, we can just actually use a 1D CNN to represent this operator. So we don't even need to, in this case, we don't even need to use fancy tools like the SwitchNet. It's just a CNN. Okay, and so the point I want to make here, this really shows that how powerful the reparameterization is. So my own experience working with the inverse problem in deep learning for about more than a year, close to 2 years, is really sometimes when you're given the data, we first need to think about how to reparameterize the data. Because if you do reparameterization correctly, then the neural network architecture becomes very simple. You can more or less turn it, in some cases, you can more or less just really turn the image processing problem, and you can just use off-the-shelf convolution neural network. Okay. Now, so let's discuss inverse map. So again, the inverse map, we study how going from D to eta. But now I have to be careful because I did the reparameterization. So really it's how to go from this to eta rho theta. Okay. Now, we said the forward map itself can be represented as A star, is A, right? So using back projection, we also know that eta is represented by this pseudo inverse. And A itself is can be represented by CNN, 1D convolution. So therefore, the adjoint operators can also be represented by CNN. So A star is a CNN. And this operator is a pseudo differential operator. So therefore, we can, for example, use BCR net to it. Okay. So by concatenating this together, take the eta, we're going to apply A star to it. So this corresponds to 1D CNN. And then we apply a pseudo differential operator. So this corresponds to the BCR net. Okay. So in fact, here is using BCR net because the performance is a little bit better. But you can actually, in fact, replace this with a 2D certain kind of convolution neural network that will also do a decent job. Okay. Now, once we have that, we get this. This gives us an architecture, and with the architecture ready, and again, we're going to train all the weights of these neural network components end to end using the training data. Let me just give you one example, and I think this is a good example, not only to show the purpose, but also show that our network is robust to noise. So here you have the setup I just described. You have the domain, you have the boundary measurement. So again, the R and S, so the seismic station, also receivers, are uniformly placed on the boundary of my domain. Okay. So the media eta x is corresponding to different inclusions. You have of different orientation, different shapes. So you can see that you have a round shapes, you have elongated shapes, and you can also have a negative inclusion or positive inclusions in the sense that a certain part of the sound speed is going to be much lower than the background, and a certain part of the sound speed is going to be much higher than the background. Okay, so here, negative was yellow color, positive was blue color, dark blue color. So the training data we have is about 20,000 pairs of eta and D, so media and boundary measurement. And for testing, we also generated about 20,000 pairs. So here's what the results look like. So we performed 3 different group of tests. One is with only negative inclusions, only positive inclusion, and the mixed inclusions. So in each case, this is the reference. I show you the reference eta exact. Okay, and this is, I didn't show you the data, but so this is the reconstruction we obtained by adding no noise to the data. So we collect the clean data D, and then from that, and apply our neural network and try to see the reconstruction. And you see that in this case, all 3 cases, you get almost perfect reconstruction for this eta equal to 0. Then we added 2% of the noise. So the reason is because usually in inverse problem, your measurement devices might be imperfect, right? You might have the noise inherently in the collection environment. So these things will add a noise to your data. So if we added 2% of the noise, and then this is our reconstruction. And you see that the boundary of the reconstruction get blurred a little bit, but overall the shape, the orientation, the magnitude remains well. And finally, we add a lot of noise, as a 10% of noise. So this travel time tomography problem is a little bit ill condition. It's not too bad, but it's still ill condition problem. So therefore, by adding 10% noise is actually very severe noise. It's actually gonna, unless the method itself is robust, otherwise the result will be very different. But as you see that in our reconstruction, we still get roughly the correct shape and orientation. And even though the boundary is much more blurred, but overall, I mean, the construction is quite successful. So therefore, this is one testing example to show you that the network that we construct is in fact quite robust to noise and quite stable. Okay. Now let's come to the summary. So here I talk about two things. One is that two contributions in this talk. The first is that we propose some new neural network modules for pseudo-differential operators and full integral operators. So these operators are very important for solving inverse problems. And then I talk about two applications. So in fact, we work out we have papers on all five applications I listed at the beginning of this talk, but due to time limitation, I give two examples. One is far field imaging, and the other is travel time tomography. Now, some of the takeaway messages, and these are really the lessons that we learned during working on this project. And the first is that it's a good idea, at least to me personally, I believe that it's a good idea to use math and physics to decide architecture of the neural network. This provides some general guideline. So here, the tool we are using is really the physics of the inverse problem, and also the filter packet projection operator. But at the same time, the data needs to be tuned, or the weight of the neural network needs to be tuned from data, from the training data, because this is really the lesson that people learn from working on various kind of AI application, that everything has to be tuned end to end to get the best performance. Another important piece of experience is that reparameterization really helps. So if the data is parameterized in a bad way, then you might need to use fully connected neural network, which is very hard to train. But if you reparameterize in the right way, then it can be simply be implemented by convolution. Okay. And finally, as I'm kind of repeating myself, it's end-to-end training is very important. And in fact, it's very flexible. And this is end-to-end training gives us the best performance. Okay. With that, I would like to thank you for listening to the talk. And this is supported by National Science Foundation in the United States and also the Department of Energy. So these are the few reference papers that relate to the work I just described. And also at the end of the talk, I also have a long list of references about various kind of inverse problem papers appeared in the literature. So I'd like to mention that I didn't describe these work, but I think it's really a big booming field. A lot of people made a contribution to this, and I'm looking forward to interaction. And I think that it's more interesting things will come to this at the intersection of inverse problem and deep learning in the coming years. Thank you.
Okay, thanks for a great lecture. And we'll come to the questions. There was a question already for some time by Yui, so please, Yui, go ahead.
Yes, well, thank you so much for the very interesting talk. I actually had two questions, but in the meantime, I figured out one of them myself. So there's one left. Could you go back to the training slide, please?
Is this here?
No, in the first application. Sorry.
Is this the one?
No, I think it's the previous slide. Yes, exactly. So you train. So you have a network that consists of sort of two concatenated parts, and one is supposed to learn something like A star, and the other one is supposed to learn something like A star A plus epsilon identity minus inverse.
Right. Yes.
So this epsilon usually depends on the noise in the data that you have.
Yeah.
It's something like this signal to noise ratio.
Right.
Is there a way to parameterize this BCR net with some parameter that you could insert into a trained network already, and that would change its performance slightly depending on what kind of input, what kind of D you give to it, what the noise in D is?
Right. So I guess you were probably asking about.
Did I make
that's a good point. I mean, so first let me clarify. In practice, when we design a neural network architecture, it's motivated by this filter back projection operator. But when we train that we do not put any information of epsilon inside the neural network. So therefore, what we do is that we just, I mean, when we get to the red line, we forget about this red line here, right? The architecture, we forget about, after we get this, we forget about how we come to here, right? And then we just use the data to train it. So you raise a good point about maybe we can tune the neural network based on the signal to noisy ratio. So what I would personally suggest is do an architecture like the following, is that you have the D comes in and you have some kind of estimate of signal to noise ratio. And then you feed both of them into architecture and see what kind of EDA can produce, right? So, so if you have a confidence into signal noise ratio. So now in the testing process, if someone give you a boundary measurement with a calibration about what the noise level into this, and then hopefully the neural network can use this noise to signal to noise with the noise information and try to produce ETA. So I would just treat this ETA as an external parameter. Okay.
Okay.
Sorry, choose this sigma, the noise level, as an external parameter.
Yeah. Thank you.
Yeah, sure.
Okay. You had a second question, or the second question was resolved? Okay. Ozan is next.
Yes, thank you very much for a very nice lecture.
Thank you.
I have a question that's a bit related, perhaps, again, to what you were asking about. So it's like I'm following him all the time. When you are essentially using the filter path projection as a blueprint for doing this.
Yes.
So you're composing the switch net with the BCR net, and then you're training that composition, is my understanding. Usually when at least one aspect that we have seen when we use neural networks in these problems is also their ability to kind of capture prior knowledge about the image that you want to recover. Without in a regularizer, of course. Here you are essentially designing the regularizer already by formulating this FTP style scheme, which is not iterative, right? So I was just wondering, is there a way to push this further than, if I would like say I want to do some kind of, let's say, optimization based regularization instead, which offers perhaps a richer set of priors. How would in that case, I would probably use A star will pop up, I guess, right? And A star A, the normal operator, would also pop up. But would that be also SwitchNet and BCRNet kind of things that I could put in there?
Right. So first, let me answer provide a little bit background about how when we come up with architecture, because the motivation that I really had is because so you can also use analogy of, for example, do ImageNet doing image classification, right? You can say certainly natural image has a very strong prior because these are what kind of picture you see. It's not cartoon images. This is not like a random noise. But when you think about the neural network training for this ImageNet data set, it doesn't need to specify any priors, right? The neural network automatically try to adapt itself to the image data prior. So that's my motivation here as well, is that in the designing phase of this project, I would think about whether I should put a prior in there or not. But I motivated by the success of all these image processing, image classification networks, I feel like maybe we don't need to specify the prior explicitly. So that's how we come up with this architecture. But now one can certainly, the tricky thing is that I don't know how to capture the image prior of this training data, because so certainly, for specific type of training data, you will be able to say a few more, like what Yuri's question is, that and what is the noise level and things like that. But in general, and I think it's a pretty hard task to capture. I just don't know how to do that. I probably don't. It's not a satisfactory answer to your question, but I don't know how to. And also the amount of data that we have is usually quite limited compared to these more data-rich applications. So trying to extract the image prior from the data is actually it might seems to be quite challenging.
Okay. Thank you.
Okay, further questions from the audience, maybe, from the physical audience, which is
one question. We do have one question in the audience.
Okay. Go ahead.
Yes, just a curiosity. like again on the training process, so maybe it's slide 23 or something like that. So I was just wondering, in the case of noisy data, do you train the network with noisy data to, yes, exactly this one. So
No, so network is trained. We did both, but I believe that this result I show you is from a figure where the data I trained it with clean data, and then do the testing on the noisy data.
Okay. Yeah. Okay. Now this is something interesting, because so if you train it with noiseless data, in principle you would probably learn something that is similar to the pseudo inverse, which actually is not solving completely the stability issue, because still you can have some instability if you just apply the pseudo inverse. So it's probably related to what Yuri was asking before, because in that case, so epsilon could be really close to 0, but then if you move to some more noisy data, that's very interesting. Sorry, I thought it was trained on noisy data, so I was not understanding this, but
yeah.
Yeah,
I mean, if you I believe it's trained on the. I mean, because this is the experiment is actually done by my collaborators, but I think, I mean, this is the picture in the paper. So I mean, I can go back and check. But I think it's trained on the clean data and then pretty on noise. But I could be wrong. So if you, I mean, I don't know who you are, but if you can send me email, I can certainly go back to the paper and double check and give you the definite answer. So not, but I think to come back to the question of stability. So here we are not really the regularized inverse is just used as a motivation to design the neural network. And as I said, once we get the neural network architecture, we forget about it. So we don't do explicit regularization for the neural network. I believe that the stability and also the robustness is really come from the fact that we have a pretty small neural network compared to the problem size. So the difference between the way we approach this and, for example, these over-parameterization regime, these image of classification tasks, that they have a huge neural network. So they're relying on over-parameterization and finding the like a flat minimums and like small generalization error. For us, we have a small network. We're still in the under-parameterization regime. So so we don't have this overfitting problem. So we're still trying to find a parsimonious model which can fit our data. This is where I believe the robustness comes in.
Thank you very much. Yes.
Yeah, it's kind of like a least square. With a lot of data, it tends to give you a robust answer.
Okay. Yeah, Emmanuel.
Yes. Hello. So
yeah,
if I understand correctly, your motivation for this architecture is in some sense based off of the filter back projection,
yes,
or some type of, yeah. So my question then, because you have these two different networks that are composed.
Yeah.
So if you look at your results, does it seem like they actually learned to approximate these components that
good question. We took a look, and vaguely yes, but it's hard to give a definite answer.
Okay.
Yeah, because in some sense, I mean, I would like to use the terminology here in, for example, computational for seismic imaging. So I mean, I worked on it a bit before earlier. So in the seismic imaging, you really have two steps. One is called for the migration, and then the other step is really called something like a post-processing. So migration is kind of like take your wave kind of signal from the data domain back to the model domain. So here we're going to do the same thing, right? The first step of the neural network, which where we carried out this switch net, is really doing the migration step, which taking the singularities or the wavefront set, using the terminology from microlocal analysis. You take the wavefront set in your data domain back to the model domain. Okay, and then once you bring them to the right location, then you can do some local smoothing, or you can do some local feature extraction. So the second step is really image processing. The first step is really related to the first fits and the physics.
That's really cool. Thanks.
Sure.
Okay, Yui, please.
Do we still have time? I don't want to abuse the time. Do we still have time for one?
Yeah, yeah, I have a few minutes. I have some time. That's okay.
So I was wondering, in the very beginning, when you designed your modules, if I understood you correctly, the idea is that you start with something linear, and then you start with something linear that mimics the physics,
Right.
and then add a few rarely nonlinearities to sort of a deeper network out of it.
Absolutely, yeah.
Yeah. So I don't know if there exists a real connection, but I thought of the work of Stéphane Mallat, where I believe he takes the wavelet transform of some complex signal, and then he applies values to the phase in that.
Right.
And that seems some very interesting results. I think he used it for sampling.
Right.
Some.
Yeah, I mean, I think that you're right that the wavelet is both here and also in Stéphane's work. And I think I have some brief discussion with Stéphane is I don't see, I mean, wavelet play both role in his work and also in this talk here, but I don't think there's direct connection. I think the problem that he's trying to address is much more sophisticated. I mean, for me, the motivation is very simple. It's because I mean, really, for me, the whole project motivation come from two things. One is the seismic imaging relationship, migration, post-processing. And the second is that if you take a look at image classification problems, right, the convolutional neural network went very far. I mean, it's a very simple architecture, but you add a little bit nonlinearity. You compose it with self a couple of times, you get very good result. So this gives me the trust that once I have a linear representation, right, and by adding a little bit nonlinearity to that, I can really enrich its representation power. But with this all said, I mean, for this slide, I don't have any theory. This is really just like play around with architectures.
So I think in one of the applications you actually had wavelets. You had a wavelet transform.
Right.
And then well, it's not exactly the same, but maybe there is a connection with the way Stéphane Mallat treats his wavelet transform and the way you treat your wavelet transforms here. I don't know, of course, because I'm not that familiar with your work on different.
Right.
Maybe there is.
Right. I think I agree with you. They're certainly related, but I don't know how to make this connection precise. Except that both are really doing using wavelets to do feature extractions. But here I'm really using something really more. I wouldn't want to use the word elementary, but as something that people understand well. I mean, from this paper by BCR, right, Berkham, Kaufman, Rojo, they told us that if you have pseudo differential operator and the wavelet non-standard form is really a sparse way to represent that. Here I'm just exploiting that fact. It's not like Stéphane's work, which is more, I think, is more sophisticated. It also relates to how the images is generated. Right?
Yeah.
But for me, it's really a sparse representation of the operator.
Thank you very much.
Yeah, sure. Thanks.
Okay, further questions? If that's not the case, I mean, let's thank our lecturer again.
Okay, thank you.
For the great talk. And I think we are all looking forward for the third part of this trilogy, which will be tomorrow.
Yeah, thank you.
Okay,
Yeah. See you tomorrow. Bye-bye.